So your choices are, well, I was going to ask this in the form of a question. But, right. So the Earth's atmosphere, we talked about 4 spheres the other day. The geosphere, the hydrosphere, the biosphere, and the atmosphere. Okay, so the atmosphere is it's relatively thin. I think we kind of saw the International Space Station kind of put in perspective how thin it is compared to the volume of the Earth. But we have gases and solids and liquids kind of in our atmosphere. So a lot of times, and I've kind of heard this as a on-the-street question, we tend to think of the atmosphere as mostly being oxygen, but it's not mostly oxygen. It's about 20% oxygen. By far, most of it is nitrogen, kind of seeing this pie diagram. And I'm going to kind of show you how we got, like, kind of 20-80 oxygen, nitrogen is mostly in our atmosphere. This is, what are the other gases? Well, the third most abundant gas after oxygen is argon. Okay, and if you're kind of familiar with elements, argon is an element. Argon actually is one of those special elements at the end of the periodic table. It's what we call one of the rare gases. Okay. So I debated, but I kind of thought this semester I want to talk you through a little bit about how Earth got the atmosphere it has, because it wasn't always like this. Now, I also teach astronomy in the fall, and in astronomy we talk about the formation of the sun, okay, and the planets in our solar system. And it all kind of came from one common, what we call nebula. So basically, the first atmosphere that the Earth had was kind of related to what was the stuff that made the whole solar system. Okay, so the first atmosphere that the Earth had was hydrogen, helium, methane, carbon dioxide, and water, which was kind of what was there to make the sun and all the planets in the first place. But that didn't last for long for a couple of reasons. Okay, that first atmosphere that Earth had, and we put this at 4.6 billion years ago because that's basically when the sun started. Okay, it went from being just a mass to being a hot mass to the sun began fusion in its core. It became a star some 4.6 billion years ago. So, and the planets started to kind of, well, I should say the planets were snowballing up to the point when the sun became a star, and then once the sun turned on, the planets couldn't get any bigger. What mass they had, they were going to keep. So the Earth did not keep those gases for 2 reasons. One is they're kind of not very heavy, and it's a gravity thing why we have an atmosphere at all. But the other thing is that the sun, early on, was really more rambunctious than it is now. It basically had these solar winds that basically kind of stripped the atmospheres that the planets would have had. So how did we get, so basically it went back to starting from scratch, okay, again, early on in the formation of our solar system when the Earth was very new. So when the sun kind of settled down into something more normal, less solar wind, okay, then actually, and the planets were kind of crusting over, the Earth was crusting over, okay, then it could actually start to, the things that were trapped in its formation could go ahead and I say burp out from the inside. Okay, today, even today, when we have volcanoes go off, there's a lot of gases that are vented from the inside of the Earth to the outside. Okay, so that's kind of how our next atmosphere came about. Okay, so again, the sun kind of calmed down. These things are heavier than helium and hydrogen, so they stuck around. Okay, so what are these things? Well, the gases in the Earth's atmosphere were water vapor, carbon dioxide, and sulfur. Okay, so still nothing that we recognize today. So the nitrogen most likely came from the same place, Earth's nitrogen gas, because it's 80% nitrogen now, most likely came from a similar place where Earth's water came from. Early on in, again, our solar system, I hate to Earth solar system, early on in our solar system there was all sorts of extra stuff kind of running around, including comets. You guys have probably heard of comets before. Comets are icy, chunky things. We still have comets, but they're out there like by Pluto, okay, most of them. Sometimes a comet will get kind of nudged and it will go near the sun and it will kind of flare and we get excited and then we'll go back out again. The flaring of a comet is just, it's closer to the sun and it's just kind of vaporizing, so. But we got nitrogen and water from early comet bombardment. Okay, so there's where our nitrogen came from. Well, we still have a lot of carbon dioxide, water vapor, and no oxygen. Well, in order for oxygen to become part of the Earth's atmosphere, and quite frankly, animals need oxygen to live, right? It actually started with the Earth cooling and the water cycle had to happen before we could get oxygen. So here's how that went, okay? The water cycle, basically, the Earth had to cool down some more, because you guys probably have an inkling that water vapor, okay, it needs to cool down before it will liquefy, and that's totally right. Okay, so it cooled down, and then we could get some sort of clouds forming and rain, precipitation. Wouldn't that be cool there, like when the first rain events started happening? Okay, so it rains, okay. The hydrological, then it rains and evaporates, okay, it rains and evaporates. The Earth cooling actually kind of tipped the scales a little bit, so we can finally, instead of so much humidity in the air, get large bodies of water. Okay, and some of you guys know that with a very, very large body of water, all the land masses used to be kind of stuck together. And we'll be talking about that when we talk about climate change. Okay, but anyway, so the large bodies of water could be home to the first life, and the first life is plant life. Okay, and so we know one of the things that plants do today are great at taking in carbon dioxide and spitting out oxygen. That's the way I think of it. I'm not a biologist. Photosynthesis, right? Okay, so took many years for that to develop. Now, the thing about oxygen, the element oxygen, is it's very chemically reactive. So most of the oxygen that came out first actually reacted with other stuff. Specifically, some of you, if you're into rocks, a lot of our rocks actually chemically are oxides of things, okay? So, there we go. So the first oxygen kind of released didn't build up in the atmosphere, is my point. About 1.5 billion years ago or so, finally kind of the oxygen that we know and love today kind of stabilized. And so we ended up with 80% nitrogen, 20% oxygen. Now we are going to talk about the water vapor in the Earth's atmosphere. Okay. So gases in the atmosphere, just gases in the atmosphere, can be broken down as either permanent gases or variable gases. Permanent gases mean that they're permanent with regard to kind of their composition, and they're kind of uniform throughout the atmosphere. So the permanent gases are nitrogen and oxygen and argon. Okay. I'll kind of draw your attention to that last column here. So you see where it says for nitrogen, it says 28.01 for nitrogen. And the column says something about weight. See, nitrogen weighs 28.01. I'm going to go ahead and put units here. AMUs. That's how much a nitrogen molecule weighs.
It's an inverse relationship between volume and weight.
Not necessarily, but yep. One other thing, and I get my night class mixed up with my daytime class. I did not mention yet, did I? Why that little 2 is there? Okay. So as maybe you know, I think I told you my background is in chemistry, so I try not to belabor the chemistry part of it. But let's look at the symbol for nitrogen is N. What's the symbol for oxygen? O. What's the symbol for hydrogen? H, yes, okay. So the symbol for nitrogen is just simply N. Nitrogen is one of 7 elements that if you were to see a nitrogen atom, here's my nitrogen atom, here on Earth it actually would be bonded to another nitrogen atom. There's 7 elements that do that. Okay, so honestly, if that's the way nitrogen is, notice we go ahead and write N subscript 2. Again, I don't mean to, like if I do this, what's that?
Water.
Water, yep, that is water. And so what that means is you have one oxygen and you have two hydrogens. Okay, so there's kind of an ugly looking water molecule. Okay. All right, so the 7 diatomic elements, while I'm at it, nitrogen is 1. You think oxygen is diatomic element? Yep, notice a little 2 there. The others go, let's see if I can, hydrogen, diatomic. I'll just do it this way. Hydrogen diatomic, oxygen diatomic, fluorine, which I don't think we do much in meteorology. Fluorine, diatomic. What's Br stand for?
Bromine.
Bromine, yep, diatomic. N, of course, that's nitrogen, diatomic. What's the element I? Not iron. Iodine, very good. You guys should take chemistry. Yep, diatomic. And what's the Cl? What element is that? Chlorine. Chlorine. Very good. Okay. And the way I remember this is, and again, this is more chemistry, but it's Hofburnickel. Like a German name, Hofburnickel. If you can remember the German name Hofburnickel and start to write it out, can you see the Hofburnickel? Okay, so anyway, diatomic elements. So oxygen weighs 32. Now, one last thing, and again, it's not a chemistry class, but we do have the elements on the wall over here. If I look for nitrogen, and you see the number 7 for nitrogen, but if I look closer, I see the decimal number 14.01-ish. Yeah. That black number, 14.00674. So if you take 14.0, let's say 14.01, and you take it times 2, you get 28.0. This number up here, this decimal number, is how much one of them weighs. So you multiply it by 2 and you get what N2 weighs. So oxygen over here has a decimal number, 16.00. If you take it times 2, you get 32.00. Now, only in kind of a small way will later on in this course, out of chemistry, back to meteorology, later on this will make a difference, a little bit of a difference, how much it weighs. All right. Whew. So the trace gases then are these, okay? One of the things I thought was interesting was a while back, helium is, maybe still should be, helium's like in shortage. Helium used to be like the United States had a national reserve supply of helium because all of the helium that Earth has is all we're going to get. We're not creating helium anywhere, okay? The sun is creating helium as it fuses hydrogen, okay? But anyway, I just thought that was interesting too. Okay, so those are permanent gases. They're relatively consistent with regard to their percentages anywhere you go on Earth, okay? Variable gases, not so much. There are 3 main variable gases that I want to talk about. So they vary, they call them variable gases because they vary by amounts and by location. I mean, let's start with water. I mean, do we always have the same amount of water vapor running around our atmosphere? No, this location varies day to day. So the water vapor is a variable gas. And I've heard it more, I'm not quite sure where the 0.25 comes from. I actually have heard it 1 to 4%. And maybe it's talking about, instead of by volume, by weight. But a water molecule weighs 18.01 AMUs. So again, putting on your chemistry hats, okay, H2O, you could look up 2 times how much a hydrogen weighs, plus 1 times how much, plus 1 of how much an oxygen weighs, and you get 18.01. Okay, another variable gas, carbon dioxide, and I'll kind of tell you why that varies from location to location and throughout the year. Carbon dioxide varies. Okay, now water vapor, we'll talk more about water vapor. You guys probably call it humidity, right? Water vapor in the air, humidity. And that's something that you're tracking, relative humidity. But your carbon dioxide, probably not tracking. I'll show you who is tracking it. And this one you're probably not tracking either. Ozone. Ozone is made of oxygen, okay? So how many oxygen atoms does ozone need? 3, yes. 3 oxygen atoms. 3 times 16.00 is 48.00. Okay. So these are all variable by amounts and location. So starting with carbon dioxide. Carbon dioxide is notorious, right? I'm going to kind of show you some graphs about carbon dioxide gas in the Earth's atmosphere. So when it says amounts over there, because on a slide here in a minute, this percent actually is going to be in parts per million. So 0.040% actually corresponds to 400 parts per million, ppm. Carbon dioxide. So of course, carbon dioxide has the reputation as being something we're concerned about increasing in the Earth's atmosphere. So we're concerned about human impact increasing carbon dioxide. But here actually, this first says, how does just Mother Nature and natural sources get carbon dioxide into the atmosphere? And one is when we breathe, that's animal respiration, us breathing. When we exhale, we give back, we take in carbon. We take in a lot of things, only percent of the oxygen that goes to our lungs do we convert to carbon dioxide. When things decay, when living things decay, it gives off carbon dioxide. And I mentioned about the burping, okay, when the earth burps. Okay. So those were natural sources of carbon dioxide in the atmosphere. The word anthropogenic means from people. So if you're an anthropologist, you study people. So anthropogenic means, genic means from, so it means from people. So anthropogenic sources of carbon dioxide, the most notorious one or whatever is burning of fossil fuels. So fossil fuels means coal, gas, oil, okay? Those are all fossil fuels. So those are ways, a natural way and a man-made way of getting carbon dioxide into the atmosphere. So here in a minute, I've got a figure to show you that actually there are definitely natural ways of taking carbon dioxide out of the atmosphere, okay? And they're kind of listed here. One, we talked about plants. They take in carbon dioxide, they spit out oxygen. Another one is just by being there. The oceans don't have to do anything. Basically, the way gases work, all gases will kind of move into the large body of water that they're hovering over. Okay, so it's a good sink for carbon dioxide. Now that is somewhat temperature dependent. Okay, so temperature plays a role on what we say the solubility of carbon dioxide into the oceans. But it's a player. So here was the figure I was talking about, where these red arrows pointing up are where carbon dioxide is going into the atmosphere, and these purple arrows going down is where carbon dioxide is leaving the atmosphere and becoming part of the geosphere. All right. So carbon dioxide is a variable gas. So here's where I'm going to kind of show you how it varies. Okay. There are 2 variations in carbon dioxide in our atmosphere. Okay, this first one goes with seasons. Okay, and it has to do with plants. So I was thinking about this the other day, and it's like if we didn't have plants, we would not see this variation. So one thing about when plants are most abundant, I think spring, right? I think spring. There's a delay though. So basically, it's not until fall that kind of the full impact of the flourishing of plant life hits. So plants are great for taking in carbon dioxide. So we see actually in the fall kind of a minimum amount of carbon dioxide in the atmosphere. In the springtime, when it's just kind of warming up and stuff like that, actually there's what we call a maximum. Okay, so there's that that seasonal trend. And then there's this year-to-year trend. So the seasonal trend is like from, spring to spring. That's the seasonal trend, 1 year. And then there's this ongoing buildup of carbon dioxide, quite frankly, in our atmosphere. I'm going to show you a figure to do that. Kind of let the figure do the talking. So it's this one, not the seasonal one, but it's the year-to-year trend in carbon dioxide increasing that gives us concern. Okay. So let's look at those. So this is a figure from your textbook, and most likely this red line actually is data coming from an Hawaiian island. And so clear back in 1960, this project was started. I want to volunteer for this job to basically every hour, I don't know how that goes, to measure carbon dioxide in the atmosphere at this one location. And can you kind of see the little blips? Okay, that would be each year. It kind of goes through one. Okay, so carbon dioxide minimum would be in the fall, maximum in the spring. Minimum in the fall, maximum in the spring. Okay, that's kind of how that goes. But you can also kind of see this kind of ramping up. I'm going to kind of step back, or actually I think if I go to this one, I'll be able to kind of show you back farther in time than this. This is just for one location. Okay. By the way, so the reason we're concerned about carbon dioxide is it's you probably heard it, this greenhouse gas. We'll be talking more about that actually in the next chapter, I think, or maybe chapter 3. But carbon dioxide is good, bad, in acting as kind of a blanket to basically kind of keeping us warm. So as this increases, then the effect of keeping us warm, we're also worried about. Oh, and I did not see if this will do it. Plug in. I went here Thursday night, and I'll see if it changed much. It must have turned out okay, but I know that this one research facility here that's maintaining this record had funding issues maybe a year and a half ago. So how convenient! Just stop measuring carbon dioxide in the atmosphere. I don't know what your problem is. I know, dramatic pause. While this is coming up, it's actually an important thing. Hopefully this comes up. Back to your projects and stuff. Now, as it snows, get your cameras ready. Okay, I just wanted to make sure we're all on the same page with your photo projects, that you need 10 different events. So like snow can be one, sunrise or sunset could be one, wind could be one, a clear day could be one. That's 4, okay? So.
Do we need to write anything about it?
And the thing about your photo project, for each photo, you just need to tell me, I think it's 3 pieces of information. Describe what your event is, so I don't have to guess. Describe generally where that photo came from, like region, and about the time or the date. So. Yay, we win. Okay. So I think it's hourly. My goodness. So here we go. A little bit ago, remember it's 0.040%. Is it by volume? I don't know. But here, that corresponds to 400 parts per million. Here, this is 402.64 parts per million. And it does kind of look like it's just kind of on automatic, maybe even more than hourly. I don't know.
Is there a reason why they picked that certain location?
The reason they picked that certain location, I think it was to hopefully be away from human activity, per se. And that location, it's funny how the islands you would think would be cloudy a lot, but they had a lot of clear, a lot of clear weather. There's an observatory there, so I don't know. So now I think if I go down here. Okay, so that's 1 week. This is 1 month. Still like, I don't see much. Let's see. Let me go down again. Maybe. This is, oh, I guess I just hover. If I hover, did it change? Well, is that 1 year? Does that look like 1 year to you guys? Yep, okay, that's 1 year. 2 years. Okay. Okay, yeah. So this is kind of what was in your textbook. Kind of the 1960 to the 2015. So anybody see the movie The Day After Tomorrow? I like it. I like it.
Makes me not want to be a news reporter though.
You don't want to be a news reporter because of The Day After Tomorrow?
Well, yeah, because he got hit by a car.
But you remember The Day After Tomorrow, how it started out, like they were like in an ice sheet getting a core, okay? One of the things you can do with those cores is if you go to the bottom of the core, actually trapped in the ice is what the carbon dioxide was clear back then, okay? So I'm telling you that, okay, this is actually more kind of getting along the lines of what they call the hockey stick. I think Al Gore might have referenced it. Do you see a hockey stick? Long, short, and okay. So this is carbon dioxide, okay, and you kind of see the squiggles there. This data actually came from the dude in the Hawaiian Islands, okay, the dude or dudettes, okay? And this right here carbon dioxide content came from a different source, okay? So the deal is, you figure industrial revolution. The reason I say industrial revolution is that's when we started doing the whole kind of using fossil fuels as an important source of energy for our lives. So maybe about the mid-1800s or so. Okay. So we've been using fossil fuels, and so this would be the carbon dioxide increase. Okay, we think most likely from that.
What is the green line?
The green line is, I think, current. Oh, I don't know, it says 400. It's either current, because 400, 402, I'm not sure. I think I did hear, I remember kind of the sad day when it went, kind of flipped from, 390s to 400. And I don't know if that was some significance there. The other thing we've been fighting, with regard to carbon dioxide increasing in our atmosphere is that we actually have been taking away trees. We use trees for different things. So large amounts of trees, or kind of forest sort of thing. And then of course the thing that forests can do can remove carbon dioxide into this one. And so then the last one I want to show you is this one, 8,000 years. You're like, really? How do we know carbon dioxide content 8,000 years ago? Well, again, I guess I probably would refer you back to something along the lines of an ice core. But you'd be like, this was way before people were here. So this is 800,000 years ago. Okay, no people, no burning fossil fuels. And look at the swings. Look at the swings. Okay? The problem comes in that if you look at where the swings kind of topped out, 300 parts per million-ish. Okay, and again, where are we today? 400. Okay. So this little bit right here, this actually is not if I was looking at this data in another sense, you might say, well, that's an anomaly. You might say, well, that's something malfunctioning in your equipment. Okay, but this actually is what we looked at earlier. This is the spike right here. This is nice. So that's kind of where we're at with regard to carbon dioxide being a variable gas.
Wow, I spent a lot of time talking about carbon dioxide. Let's see. This is kind of, I was looking at my notes this morning, I'm like, aerosols? Where did that come from? So it feels like it's just kind of inserted there. Okay, aerosols would be a variable, they're not a gas. Aerosols are suspended solids and liquids. And I have kind of a cute little thing down here. When I thought about aerosols while I was putting together this slide, I thought of this one with, what is this, is it Mud? What's his name?
Oh,
Who's the, is it Linus with it?
Linus.
Yes.
Okay, but it's just adorable. So one of the things about dust is that actually is an aerosol in the Earth's atmosphere. Yeah. And it can cause it to, it can obscure your visibility, okay, to distant objects. Dust and that sort of thing, actually, I think I might have mentioned when we talked about Mount St. Helens spewing the particles, dust and ash can actually help cause cloud seeding. So there's a good thing for that. So I have a couple pictures here. This is anthropogenic dust here, air pollution. We're kind of looking at the region of China. Okay, so here we have air pollution. Okay, and here we have a natural source of dust, a dust storm. And then kind of to end that thought, around here, if I guess I think of more in the fall when the farmers have their combines out, and if it's been kind of dry, okay, you can almost in the morning see kind of the haze, okay. And actually that haze or the presence of dust particles can give an extra brilliant sunrise or sunset. So I think we got time to knock out ozone. Definitely not going to get through chapter 1 today, so I'll bring chapter 2 on Wednesday. So ozone is 3 atoms of oxygen that are stuck together. There is good ozone and then there is bad ozone. One of my, and I hadn't patented it yet, but one of my things is I think we should be able to take our good ozone, take our bad ozone, which is here, bad ozone, which is here, and we should pipe it up to this location, to our good ozone place. Okay, I'm going to talk about the ozone hole. That's why I think we should replenish our ozone with bad ozone. Okay, so good ozone is in, I'm going to wait till Wednesday to talk about this, but it's a layer called the stratosphere. We'll talk about what the stratosphere is. Okay, so good ozone is in the stratosphere. It's in a particular layer of the atmosphere. And the thing about good ozone is it can be chomped away by CFCs. And CFC stands for chlorofluorocarbons. Bad ozone, it'd be like, I don't know. So if you're driving down the road, sometimes I've been kind of going back and forth, the St. Louis area, and I'll see these signs, okay, for big cities, and it says ozone alert. And I just want to emphasize that ozone actually can be a secondary gas or secondary pollutant from regular factories. Yeah. So if you have asthma, yeah, cities have bad ozone. Ozone also can be created actually under the high temperatures of lightning strikes too. Anyway.
What happens with the bad?
The bad ozone, it just makes it harder to breathe, especially if you have a condition that. So we have bad ozone. Yeah, it's safe, but like I said, some people are more affected than others. Makes you glad you live in Keokuk, Iowa. Okay. So I think these next few slides kind of go together. So you can write down this, but I'm going to start with these few. I'm going to finish up ozone on Wednesday. I'm kind of running out of gas. So we'll finish up ozone on Wednesday. One quick slide about water vapor. Go to the structure of the atmosphere. Talk about pressure and. So I think we'll start chapter 2 on Wednesday, but I know we'll get through chapter 1 on Wednesday. Any questions?
Do you want chapter 1 on Wednesday then?
If we get, chapter 1, the earliest to be due is Friday. Was that your question too, Blake? The chapter 1 will be due Friday. Just count on it. Yep.
Okay.